Hi, Shantanu. So we are live now. Yes. So hi, everyone. Hello. Thank you so much for joining the session so early in the morning. So Atul, Shantanu, I think we'll just give it 1 minute and let whoever join, and then I will introduce him.
Yeah, I see people joining, so maybe we can just wait a few more seconds.
Correct. Sure. Hello, everyone. So I think we have about 30 people in the session now. So I'm going to start the session. Good morning and welcome to the tutorial 2 of CORDS command. This tutorial is titled as Cryptographic Techniques for Data Processing. This will be presented by Shantanu Sharma, who is from New Jersey Institute of Technology. And this tutorial mainly focuses on recent advances in the secure cloud-based data, outsourcing based on cryptographic and hardware-based approaches. So I will hand it over to Shantanu and he will take it from here. Shantanu, please start. Yeah.
Okay, thank you, Madhumita. And now let me share my screen. Can you see the screen now?
Yes, we can see the screen.
Okay, so if you find any question, I cannot see any window here except this window. So if you have any question, please let me know and I will answer at that time. Okay, and should I start now?
I'll do that. Yes, please start.
Okay, so thank you very much for having this tutorial. And as Madhumita told, the title is Cryptographic Techniques for Data Processing. I am Shantanu and I am from NJIT. Another speaker, Sarath, somehow he is not able to manage today. Some emergency came, that's why he is not here. I will cover his part also. So at the very high level, I will first cover introduction about cloud computing, why we need security, what are the 3 different techniques we can categorize cryptographic techniques, and then I will go in little bit details about 2 important cryptographic domains, encryption and secret sharing based techniques. Then I will go over the how we can use trusted hardware like Intel SGX, and finally I will go over the how we can scale the cryptographic techniques for very large size data over either hybrid cloud scenario or the public cloud scenario. So let me start with some known thing that we all know since last at least 1 decade, the cloud. So these days we all use cloud for our in daily life. For example, storing our documents on Google Doc or OneDrive and so on. Why? Because they are very cheap and they provide us availability 24 hours. Chances are very rare that we cannot access our online documents. And we don't need to pay a lot. So this is the most advantage of using the public cloud. And we don't need to build the infrastructure and maintain all the hardware and time to time software maintenance. So this is the best thing of cloud. Generally, we can categorize cloud as public cloud. Amazon, Microsoft, IBM, they provide public cloud, and we use these clouds very frequently. Private cloud, like our university-based system or office system, that they are internally keeping and not using any outsource access to that system. Hybrid cloud, in between these 2 things, some parts of the data is in or the computation is and at the private side, and some part on the public cloud. And all these clouds have different challenges in terms of using those clouds, like in using storing data, performance and security things. And I will go over only on the public cloud mostly. So what are the challenges when we use public cloud in terms of security, and why security is the most important critical thing there? So the part is this: there are several servers, but they are shared by several people. Not only I am accessing, millions of users are accessing those systems, and it is not providing us capability just like we are accessing our personal laptop, that no one can access our system. So once we are using a system that can be accessed by millions of users, so there is not the same level of control on the server side or the system that we are using. Another thing is this: even if we assume that okay, something will be there at the cloud side, at the public cloud, some security mechanism or privacy mechanism will be there, but they are owned by some companies like Amazon or Google or Microsoft. There can be chance of insider attack, means the employees of the Amazon or Google, they can do something with our data, so still they are not completely secure. And insider attacks are not, we can say, they are not very common. We have seen insider attacks can happen. And whenever we send our data to public cloud, so we need to deal with insider attack as well as the outsider attack, means the system that is shared by millions of users, they are outsider for those cloud server, and we need to keep our data or computation secure at that time. That's why security and privacy of our data that we are storing at the cloud, right, this is very important. So we can say what is the gold standard solution. So the only one approach is okay, encrypt your entire data set, store at the cloud side, and it will be secure. And we think that okay, this will work, and because we are using some cryptographic techniques, no one can access it. But there are some chances that still people can access our data, and they can see what is happening over our data. And I will go over this part in the tutorial in detail, that how they can see what is happening over the data, and what are the techniques that are that have been developed for executing some computation over the data at the cloud side while the data is in encrypted manner or using some type of cryptographic technique. So before I go in detail, so let me tell you that here I will present only in 90 minutes this tutorial. So if you are interested in details of this tutorial, you can find slides on this given link, and there are around 3 hours tutorial video for the same tutorial in much more detail, and you can find these at YouTube. So let's start with the encryption part now. As I told you that the easiest way, use any encryption techniques, symmetric cryptographic, asymmetric cryptographic techniques, encrypt your data, upload to the cloud, and it is completely secure, because just assuming that adversary or the public cloud or the any person at the cloud who can access our encrypted data, they cannot break the encryption key. So under this context, our data is completely secure. We have outsourced our data in encrypted manner, and whenever we want to execute a query, what we can do, we can download the entire data, decrypt at our local site, execute the query, and our purpose is done for the query execution. But this approach is not very good, and it is not utilizing the cloud for our purpose. We are just using cloud to store our encrypted data. Whenever we are executing a query, we need to download entire data, decrypt it. So user is only performing entire operation. Cloud is not doing anything. So this approach is completely not feasible. So what are the two major categories that we can think about it, and that are there in the literature? So first one is the cryptographic techniques, that is you can see on the left hand side. So here database owner or the user who has the data, they encrypt the entire data set, upload the encrypted data to the cloud as in the previous case. But now instead of downloading the data, they encrypt also their queries. And queries are encrypted using different types of cryptographic technique that can support different operation over the data, such as selection, aggregation queries, or join queries. And cloud executes these encrypted queries over the encrypted data, and based on this, whatever is the result of the query, it returns to the user. So instead of returning the entire encrypted data, the cloud can return a subset of the answer set, or exactly the answer set that is for the query. and the user needs to just download that part instead of downloading the entire data set and decrypt it and get the result. So this is the very high level description what happens when we execute cryptographic approaches over our encrypted data. Another category is this, we can use trusted hardware. So around 5 or 6 years before, Intel introduced Intel SGX secure guard extension. That is a secure hardware based thing. So everything is happening as same, just like the previous case. The database owner is encrypting their data, uploading to the cloud, and they are also sending the query in the encrypted format. But now the query is execution at the cloud side is not happening over the encrypted data. What is happening here in the case of SGX? SGX read the data, the encrypted data, decrypts it inside Intel SGX, and then execute the query after also decrypting the queries. And it is assumed that no one can see what is happening inside the SGX, means whatever the data that we get inside the SGX secure hardware after decryption, no one can see, only SGX can see, and user can trust that no one is seeing some what is happening inside the SGX or the data in the clear text. And then the clear text based database processing, as we do in the normal databases, that we can process it in the SGX, and SGX can return the answer to the user. So this is the way that we assume that secure hardware will work, and Intel SGX tries to provide this type of functionality. So you will see in little bit detail that what SGX is providing and what is still not there. So when we see these two types of technique, but why we are designing different types of cryptographic technique, what are the objectives, and what types of adversary we can think about it. So at the very high level, we can classify adversaries into two categories. First one is the honest but curious adversary, and the second one is the malicious adversary. So honest but curious adversary is considered as they will store our data in a completely secure manner as whatever we are sending to them, and they will execute our queries whatever we are sending to them, and they will return the answer. They will not change our data, they will not change our query, and they will not delete our data. So they are doing their whatever operation is asked from the server, they are doing completely in a correct manner. They are not tampering with our data or the queries. But here they are still trying to learn your data without tampering with your data or doing anything with your data. And they can do based on several types of side channel attacks or leakages, such as ciphertext, means the encrypted data set, or encrypted queries, what types of queries we are sending, workload attack, or access pattern. I will go over this thing in the next two slides, that what are the meanings of these different types of attack. The another adversary is the malicious adversary that can do whatever they want. They can delete our data, they can change any row, any cell value of our data, they can change our queries, they cannot return entire answer. So this is completely up to them. They can do whatever they want. We cannot assume, okay, this type of adversary cannot do whatever thing we don't want to adversary is doing at our data. So designing a cryptographic technique that can deal with malicious adversary, this is extremely hard part, and we will see, okay, why this is going very hard. So just the part that I told you in the last slide, what are the meanings of the side channel attacks, and when we consider honest but curious adversary, how they can learn from the data while they are not changing anything, not tampering with the data, just query execution or the storing the data, it can itself reveal to them about our data set. So several types of side channel attacks or leakages can happen, as you can see in this slide. So let me go over all these leakages or attack one by one in a brief manner. So first one is ciphertext attack, means whenever we store our data at the server side and using cryptographic techniques, the cryptographic technique itself can reveal about the data. So for example, it can reveal the distribution of the data, means how many employees are working in computer science department, how many employees are working in electronics department. The encrypted data can also reveal the ordering of the values, means if from the data itself, it can know where is the maximum salary of the employee, which is the minimum salary of the employee. So this type of leakages or attack can directly happen over the data without executing any type of queries. So this is known as ciphertext representation based attack. So if we use cryptographic techniques that are not secure against these types of attack, they will definitely reveal something about our data. Next attack that you are seeing here, five attacks, they are based on the query execution. So what query can reveal about our data while adversary is executing our queries in a completely correct manner. So first one is the frequency count attack. So let's say I want to execute a query and it is fetching, let's say the query is fetch all the rows of John and it is fetching 5 rows. So adversary will know, even ciphertext data is not revealing how many Johns are there in a one particular organization, but the query execution will reveal that okay, there are 5 Johns if server is returning 5 rows. So this is known as the data distribution that is revealed from the frequency query execution, and eventually it will reveal the entire data distribution if we execute queries for every values. Then workload skew attack. What happens here? Let's say for some day there are many queries for IBM in one day, and another day the most of the queries are coming for Google. So based on this query execution pattern, some queries will access one day, most of the queries are coming for IBM. So adversary will see this thing that whatever rows have been accessed in on the first day of the week, they are definitely from IBM because this day something big happened in the IBM. That's why people are accessing IBM rows, most of them. So based on this type of knowledge that adversary acquired from the background, adversary can know which queries user is asking and which rows are satisfying for these queries, while query is encrypted and data is also encrypted. The output size attack, this is similar to the frequency count attack. So whenever we execute a query and return the number of rows to to the user in terms of query execution, based on the count of rows, adversary can know how many rows are satisfying for a particular value, the query keyword, and it will again reveal the data distribution. The next one is the access pattern and the search pattern attacks, and they are related to each other. So whenever we access a query, simple selection query, for example, send me all the rows of John. So here adversary will access some, let's say John are there in 5 rows, first, second, third, fourth, fifth, just assume it. So adversary will see which rows user is the processing is accessing. So the processing accessing is the first row, second row, third, fourth, and fifth. So adversary will definitely know at that time. Instead, in a very large data set, assuming 1 million rows, only these 5 rows correspond to John, and all the other rows are not of John. So these are known as the access pattern attack. The adversary knows exactly the identity of the query keyword, which rows of the entire data set correspond to the identity in the encrypted data set. The search pattern attack is also similar. So here the adversary maintains the history of the entire query, that when the John queries were executed, which rows will be fetched by the user, when when the queries for other keywords, for example Adam, were accessed, which rows was accessed. So the adversary will maintain the entire history for the queries, and based on this, whenever we delete some rows or insert some rows, adversary can know something more about the data. So based on all these types of attacks or the leakages mixed with each other, for example, search pattern is mixed with output size or access pattern or workload attack, they reveal almost our data in clear text, or at least 90% of our data, as research paper showed recently, to the adversary. So techniques are still not very secure against different types of leakages or attacks. So as I told you at the beginning that there are two types of cryptographic technique that are designed to deal with these types of attacks and leakages. And first of all, we can classify into two domains. First one is the encryption based technique, and another one you will see in the next slide, that is the secret sharing based technique. So multiple encryption based techniques have been developed. These are just I am mentioning only some of them. So first one, very popular techniques are fully homomorphic techniques that can support addition and multiplication over the encrypted data. So whatever we will perform the addition operation over the ciphertext, and whenever we decrypt the answer, this will give me the correct answer of the addition. And but they can provide, so based on addition and multiplication, we can solve most of the computation. But the major drawback of these techniques is they are not very efficient. They take significant computation time. On the other hand, there are other techniques such as partially homomorphic. They can support either addition or multiplication of the ciphertext values, but they cannot support other both operation, addition and multiplication, unlike fully homomorphic. But they are still little bit practical as compared to fully homomorphic techniques. Other techniques for operations such as using the search over a data that we want to fetch the rows or perform the join operation. Several techniques have been developed, such as I will cover bucketization based technique that can support most of the queries, searchable encryption that have been introduced in 2000, and different types of searchable encryption have been defined after that. Index-based retrieval, such as we perform in our clear text database processing system B-tree, so how we can develop secure indexes. Then order preserving encryption techniques, such as maintaining the order over the salaries or age, so that we can directly execute maximum, minimum, top k queries. Then other select search method for conjunctive search or disjunctive search, how we can perform these types of different searches over encrypted data. So all these techniques have different level of security. They are not so some of them can provide security against let's say frequency count attack or output size attack, but another one is supporting security against access pattern attack. But all these techniques cannot support security against all different types of attack. And if we want to design a technique, encryption technique that can support all, that can prevent all types of leakages or attacks, then they are not very practical. All these techniques cannot support whatever operation we want to do. So some techniques can provide, as I told you, join operation, someone can provide aggregation operation, someone can support only conjunctive search, someone can support only simple search operation. And as I told you that they are also supporting different levels of efficiency, so all are not at the same level of scale whenever we execute the computation. Another part is the MPC based technique or secret sharing based technique. So this is a little bit different as compared to secret sharing based technique. So here the database owner, instead of encrypting their data using any standard either symmetric encryption or the technique that I showed you in the last slide, here a database owner creates secret shares, some special type of representation of the data, and they outsource their data, the secret shares of the data, to multiple clouds, more than one cloud, and these cloud store the secret shares of the data. And it is assumed that if these clouds will not collude with each other, then these techniques, secret sharing based techniques, provide the highest level of security of the data. Means in this category, our techniques can be secure against the quantum computers. So quantum computers cannot also break if the data is in secret share format, under the assumption that the cloud will not collude with each other. And here the classical standard secret sharing techniques have been developed by Adi Samir in 1970, and recently several startups in the United States, they are focusing on building secret sharing based database system because of the highest level of security property provided by these systems. And on the right hand side you can see different types of recent secret sharing based techniques and system developed by the startups. So, as I told you that these techniques provide security against a very powerful adversary like they are secure against quantum computers also, and such type of security is known as information theoretical security. And these techniques can be made secure against access pattern, means adversary cannot observe which row are satisfying the queries. However, these techniques are not very efficient. They take much more time as compared to encryption based techniques. So on a landslide, if we want to see where these techniques are there in terms of different types of attacks. So first part, as I show you in the very beginning, if I download my entire data set, this is completely secure against all types of attacks. There will be no ciphertext based attack if we are using a secure ciphertext technique, and there will be no output side, no workload skew attack or access pattern, search pattern. Different types of attack will never happen. But this technique is not practical because I am downloading my entire data set. Another techniques I have not defined that what is deterministic and non-deterministic means the technique that is revealing the distribution or the technique that is not revealing the distribution, known as non-deterministic technique. They are not still secure against all types of attacks. So, and there are even the secret sharing based techniques or multi-party technique, just you saw in the last slide. They are also not secure against all types of attack. Output size attack, it can also happen. Workload skew attack can also happen. So this is a problem while when we deal with the different types of cryptographic techniques. And another part is this: even they are not secure against different types of attack. Still, they are not able to support different types of operation as we want to do over our data set. For example, first of all, efficiency. As I told you multiple times, these techniques are not very efficient. Some techniques are required to read the entire data set. So we need to read from the first row to the last row, and then they can provide our results. So this is not very optimal strategy. Some techniques are indexable, but they require multiple rounds to between the user and the cloud to traverse the index. So there is not a very efficient searchable indexable technique in there that can search over the encrypted data just like we are searching over the clear text data. That B tree can traverse. We can traverse the B tree by its own. So this is not there. There is no such technique that can support all types of database operations such as selection, range queries, join, and different types of aggregation operation. Different techniques can support different operation, but not all the operation. When we the situation come to the dealing with dynamic operation, that inserting new data, deleting some data, or updating some data. So again, this comes with okay, we can do very easily, but what about the operation? Can we do the operation after that, such as selection, range queries, or they will not reveal any relation between the older data and the new data? So this is still not very efficient for in terms of cryptographic techniques. Another part is the client side execution. So these techniques are designed to perform some types of operation, but how much client is performing to execute the query, and are there multiple rounds of communication, or client is doing most of the work at their side, client is doing downloading half of the data set and then decrypting it and then getting the answer. So how much work client is doing, this is also important criteria when we think about the cryptographic techniques. Our objective is this: client needs to do minimum operation, just encrypt the query keywords or whatever query is this, and he needs to decrypt only the query answer. But it is not very practical that and very good technique can support this type of operation. Client needs to do something more. So can we develop a technique that can in which client is doing minimal work? This is still an open question. And security, this is a most common question right now. We don't have a technique that can provide us all types of security that we want and still is very efficient. So can we design a technique that is secure as well as efficient? This is still an open challenge. So whenever we design different cryptographic techniques, either in secret sharing domain or encrypted domain, we need to deal with these five issues in the different cryptographic techniques. So before I move forward, is there any question? Because I cannot see anything here on my window.
Shantanu, till now there is no questions. If there is, I will pose
Okay.
them to you.
Okay. Okay. So I continue from here. Okay. So next thing is can we use trusted platforms, as I told you in the beginning? So first, right now I cover two categories of the encrypted techniques, that encryption based and secret sharing based techniques. So now, can we use trusted platforms also? So the easiest trusted platform is hybrid cloud. Some data is at the private side and other data is at the public cloud. So if we can partition our data into sensitive and non-sensitive parts, so we don't need to outsource our sensitive data to the cloud. We can keep only non-sensitive data at the cloud side, and now our computation can also be distributed in this way. Even whatever thing can happen at the cloud can never know what is happening at the private side, and our computation will be completely secure. So there are some work based on this scenario when we partition our data over the hybrid cloud and perform the computation over two different clouds. Other one is the secure hardware, as I told you in the beginning. The database on encrypt the entire data set. SGX will read the data in the inside the secure hardware enclave, decrypt it, execute the queries. After decrypting the queries also, and return the encrypted answer to the user. Several systems by even the industries such as Microsoft, they have developed a system using Intel SGX, and several systems have been developed by academia also. But here, when we deal with trusted hardware, there is a challenge that the size of the trusted hardware, this is very small. This is only 90 MB. It cannot store data more than 90 MB. Recently, there are some progress that we can store data little bit more than 90 MB, but still it cannot process terabyte or petabyte of data. We cannot store in the main trusted hardware or secure enclave. So how we can minimize the data movement? If we read the entire data in the SGX, then it is not secure. If we read some part of the data inside SGX, then adversary can see which part is corresponding to the query. So how we can minimize the data movement while achieving the privacy? This is the open challenge, and we right now several people are working on this part of thing. Then if we are dealing with several different types of complex SQL queries that involve such as nested queries or complex join, how we can deal these types of queries, this is still an open question. Simple queries we can deal very easily. If we are joining multiple relation, let's say 10 relations and more, there is not a very efficient solution that we can deal with in secure hardware. And also at the same time we can deal with the side channel attacks, as I told you. Moreover, these trusted hardware wares such as Intel SGS, they are also susceptible to different types of side channel attacks, such as based on the cache line or based on the register label access or some other thing, how we are accessing the page table. So system level attacks can also be happen over the secure hardware. So now in this category, we need to deal with side channel attacks happening by accessing the data from the disk to the SGX enclave, and then deal with the system level attacks when we are executing any type of computation. Next thing is, now we have three different types of category: encryption, secret sharing, and secure hardware. And of course, clear text database processing is there. So where we are standing in terms of query execution performance. So here, to measure the impact of different techniques, I took 1 million rows of TPCH benchmark and line item table, and I executed a query to just fetch one single row, not single row, one single predicate, and it was resulting to fetch 8 rows from the table of 1 million rows. And now you can see the difference between different techniques. So DESC is referring to the searchable encryption based technique. For SGX based techniques means secure hardware based technique, I took opaque, and MPC based techniques are secret sharing based technique that provide the high level of security. So the higher level of security is coming at the very high performance overhead, approximately 1000 seconds. So they are not very scalable, even in a simple selection query, as if you compare to the clear text processing. SGX based processing, they are still not very efficient. They are taking almost 100 seconds. So these slides can tell us that there are techniques, but still achieving the same level of performance as we have in the clear text database system. This is not there. So we need to still develop efficient technique that can achieve the same level of performance or little bit similar as the clear text database system. So how we can do it? Is there any way that we can achieve little bit closer to the clear text based processing or not? So this is the major question, that can we design a better technique that is secure as well as efficient for the cryptographic operation? So idea is this: yes, we can do it. We need to partition our data into two categories, sensitive and non-sensitive. And always, instead of encrypting our entire data set of petabyte or terabyte data, i- just encrypt only sensitive data. And often we assume that sensitive data is not very large, because we don't know technique that can deal with two different flavors of the data, sensitive and non-sensitive. That's why we encrypt the entire data set and outsource to the cloud. Instead of this, the better thing, only encrypt sensitive data and outsource our non-sensitive data in clear text. It will provide much more scalability. So here is just one simple scenario that we can see here. So red dots are representing sensitive data and the green dots are representing non-sensitive data. So if we can partition, only red dots required to be encrypted and non-sensitive data can be in clear text. But if we have this type of situation, since the dataset size is reduced, over which we need to execute the cryptographic operation, of course we will get higher performance, but there are additional leakages can happen over this type of computation, because now we are accessing two different data sets that are at the same cloud. So how we can overcome different types of attacks and different types of what different types of attack can happen over these two data sets. I will go over this part, and to achieve the security against these things, in addition to achieving the security against the side channel attacks, as you have seen in the previous slide, we need to deal with two new things. That is, first is known as non-linkability. Means during the query execution, adversary cannot relate anything between the encrypted data and the ciphertext and the clear text data. That means two values, in one is in the encrypted data and another one in the clear text data, they are relating to the same value. Adversary can never know this part based on the query execution. And moreover, whenever we execute any query over the encrypted data, adversary cannot relate any relation such as greater than, less than, or equal to among the encrypted values. So these are the two additional challenges that we need to deal when we partition our data. So now I will go over the second part of the tutorial. It is 40 minutes, so I will go very quickly over the cryptographic techniques. If you have question, please stop me and I will answer at that time. So encryption based techniques, as I told you, there are two categories, encryption based techniques and secret sharing based techniques. You can see here there are many techniques and I listed only some of them. Based on both techniques, either encryption based techniques or the secret sharing based techniques, multiple systems have been developed by both academia and industry. And several systems are in use, such as Microsoft Always Encrypt. We can immediately download it and use it for our purpose. So I will go over only three techniques: bucketization, searchable encryption, and a high-level idea of secret sharing-based techniques. On these types of data, either secret sharing, SGX based, or encrypted data, our focus is how we can execute simple database queries that we execute over clear text, such as selection. I want to fetch all the rows where name is Alice, or join queries, join these two tables where the department ID in these two tables are identical, or aggregate queries, count the number of employees working in D1 department or D2 department. These types of queries are the major focus, how we can execute. So this one is the searchable encryption. This is the first technique that is there for just searching a simple keyword over a data. So just assume there is a data set that is containing three columns: ID, department, and some comments. So first thing is we need to encrypt our data set. So let's say there is a single, I consider one cell, that is WI, and we need to repeat the entire process over all the cells to encrypt our data. First, we encrypt this encryption techniques using a deterministic encryption, such as any symmetric encryption technique. We can use it and encrypt the data. This will also work as an encrypted query. In cryptographic literature, we call it trapdoor. So it will also work as encrypted query or trapdoor whenever we want to execute a query. So now, next step is after encryption, we need to partition our encrypted ciphertext into two parts. One is the n minus m bit that we call as left bit, and the remaining m bit as the right bit. Next thing is we generate some keys. So we apply a some function. The function is identical for the entire table. Over this function, this is a pseudo random function, and we take the input as li, execute the function. It produces some value ki. Next step is we take some pseudo random string. The length of the pseudo random string is the same as the left bit, that is n minus m bits. And on this si pseudo random string, we perform the same function that we perform over the li under the key that we have generated in this this orange color box. And now it will produce another value that I am denoting as ti. Next step is just perform the XOR over all the m minus m bits of li and n minus m bits of si. Bit by bit, we are performing XOR operation, and the same thing we will perform XOR operation over the m bits of ri and ti. And this is the value that we will get n bits. This will behave as a ciphertext that we will outsource to the cloud. So here the left hand part that you are showing very small. This is the processing we did when we were outsourcing our data to the cloud. So we generated the data using some applying some function, and finally XOR operation. As I told you in the previous slide that EKWI means encrypted ciphertext representation for one particular word. It will work as a trapdoor. It is here, not because we want to search the same trapdoor over the data. And the idea is this: if we have three numbers a, b, c, and such as the out a, and we are performing XOR between a and b, the output is c. Now if we perform XOR between any two values, either a and c, we will get definitely the third value, or b and c. If we are performing XOR over b and c, we will get a. So the same idea is we will perform over this encrypted search at the cloud side. And we will perform the same operation as we did at the data outsourcing part. So this operation that you will see in this slide, this operation is done by the cloud, and you can relate it that cloud is performing exactly the same steps as the database owner did. So first part, in the last slide you saw that we partitioned our data into two parts. So the cloud will also partition the query trapdoor into two parts, n minus m bits. As you can see in green color, this is represented as E1, and the remaining m bits are denoted as E2. It will also partition each cell value of the data set into two parts. I am denoting as CTLI and CTRI. Clear text left part and ciphertext left part and ciphertext right part. Next, recall that on the left hand part of the encrypted part E bit or the li bit in the last slide, we perform the encryption some function. Here again the cloud will perform the same function. And furthermore, it will perform, because there we generated a pseudo random string, but now how we can generate the cloud can generate the pseudo random string. So pseudo random string will be produced by the XORing the value of E1 and CTLI. And here you can see this thing in the small picture that you are seeing on your left hand side. The ciphertext is produced by the XORing the li bit and si bits. So if we perform the XOR operation over the E1 bit, that is identical to li, and the ciphertext CTLI bit, it will definitely produce the si bits. Now over the si bits, the cloud perform the same operation, the pseudo random function with the key ki, that he has generated, and it produced some value, as you can see, TI. Next thing, we performed the Xor operation when we were outsourcing the data. So between the RI part and the TI part, see your left hand side in the slide, in the bottom. Here we are performing the same thing. So E2 and CTRI, they are XOR and matched against the TI bit. And the cloud will check if they are matching. This is correct. The cell value is matching the query keyword, and send this entire row or whatever is the query, return the value to the user. Otherwise, this is not matching. So this way searchable encryption techniques work. But here is the problem. First, see the problem that we need to read the entire data set. So if data set is very large, this is not very efficient technique. There is no support for index, and it takes significant time. The advantage is here is this: the adversary cannot learn anything about the data, that the data distribution from the ciphertext. It cannot learn. But this technique is, on the other hand, is not secure against output size attack or the access pattern attack, because adversary can know which rows are satisfying the query and how many rows are satisfying the query. So then the question is that can we design indexable searchable techniques? So instead of reading the entire data set, can we develop some technique that we need to read a small amount of data? And there are some techniques that can provide indexable searches. They build some encrypted index, and user can search based on the encrypted index. But here are some challenges or some problems that we need to deal with whenever we deal with indexable searchable encryption. First thing is, who will generate the index? Most of the approaches, they need database owner needs to generate a secure index and then outsource to the cloud. So this is a question: if database owner is also executing the encryption over a data before outsourcing and then creating index, this is overhead at the database owner side. So often we want that a technique that can develop an entire index at the server side instead of the database owner side. And then the next part is how we can traverse the index. Most of the time, if we will ask a user want, okay, I don't want to traverse the index and I don't want to be involved in that index traversal. But some techniques are there that requires several interaction round between the cloud and the user. So cloud is not aware how he can traverse for a given query. So for every level of the tree, the cloud needs to interact with the user, and then they can traverse the index. And this is, as you can see, if cloud is asking for every level of the tree, this is not very efficient technique. Next part is the how we can update the index if something is changing in the data set. Then index update. This is a problem. So if the user will download the entire index and rebuild the entire index, will cause significant problem at the database owner side. Or if the cloud will build the entire index, then the cloud will know the underlying data. So how we can deal this issue, that cloud will develop the index, rebuild the index while without knowing the what are the inside in the database. So early there are recently some approaches are there where still most of the techniques are considered DB owner will generate the data. So this is still unsolved problem, that how the server will generate the index and without knowing anything about the data. But early approaches were asking, okay, for every index traversal, user needs to do multiple rounds of communication between the from the server, and they were not supporting any update operation. However, recently in ICT 2017, so people start working on the update part, that how we can update the index and we can avoid the interaction between the user and the cloud. But still, update operation is not very efficient. We can update only some limited time. If we want to update lots of information in the index or over the data, this is not very feasible. Eventually the database owner needs to download the entire index and rebuild the entire index and outsource it. So this is updatable index or updating an index. This is still an open problem. I am not going over about any technique, how indexable techniques will work. So this is in the detailed tutorial you can see. The next techniques that are known as order preserving secret sharing technique, order preserving encryption technique. So here the idea is this: if there are two values, let's say A and B.
Shantanu,
Hello.
hi. So I think there is a question in regarding the
Uh-huh.
searchable encryption. So the
Mm-hmm.
question is that in searchable encryption, any
Mm-hmm.
recommended values for n by m are there? Are these fixed or can vary based on the choice of encryption function? So the recommended values for n by m is the question.
Uh, N by M. 1 minute.
I mean n m.
Okay. So this is okay. Yeah. Okay. So here n and m bits. So there is a prescribed criteria that how many bits we can select in n parts and how many bits we can select on the m bits, because this is driving the key for the ki part. So this is not okay. We can take only minus m bits is equal to 1 bit, and m bit is the remaining data, remaining entire data set. So this will not work. So this is a particular criteria for selecting n minus m and the m bits. We cannot randomly select it.
Okay, sure. I think you should go ahead for the next technique. Yeah.
Okay. Okay, so here, if I was telling about order preserving encryption techniques. So if we can compare two values in clear text, such as A is less than B, so we want to develop an encryption technique that can also support the same type of operation over the encrypted part, the ciphertext. So the cloud can, without asking user or any type of interaction from the user, the cloud can itself know that encrypted part of A is less than encrypted part of B. So these types of techniques are known as order preserving encryption techniques. And here you can see this part, that if cloud can know which values are less than, which values are greater than for a given thing, we can efficiently execute range queries, and as well as we can execute maximum, minimum, or top k queries. This concept was introduced in Sigma 2004 by Rakesh Agrawal, and after that, several papers have been developed over the efficiency issue over of order preserving encryption. Along with developing the papers for the order preserving encryption, since these techniques are revealing the order of the one particular column of the database, several attacks have been discovered when we use order preserving encryption techniques over a data set, and there are bunch of papers are there. Basically, these papers are saying that if we are not very careful using order preserving encryption techniques over our data set, this will happen that by just using those techniques and outsourcing the data and without executing any query, adversary can see our data values in clear text by just efforting some collecting background knowledge. He doesn't need to decrypt anything, but he will actually know real, clear text to ciphertext mapping. So these techniques are not very completely secure if we are not using in a proper way. So until now, I have very high level figured out what are the point queries we can execute using the searchable encryption techniques, and there is a way to do using the indexable techniques, and we can also execute range queries using the order preserving encryption techniques. There are two queries I left: join and aggregation queries. So, in the beginning, I told you that bucketization is a technique that can solve most of the queries. So, here is a very high level idea of bucketization. So, let's say this is a table for name and salary, and I will first database owner wants to create a buckets over this data. So what database owner will do? It will, let's say I want to execute queries only for salary part. So I will create buckets only for the salary part. So it will partition the entire salary range. Let's say the salary range is database owner is considering from 30K to 160K. And for each different range, it allocates some random IDs, as you can see on the right hand side. Now, whenever we are encrypting our data, over the entire row, we can execute any encryption techniques such as symmetric encryption or asymmetric encryption. And whenever we have any particular value of the salary, let's say 54,500, we need to see this our bucket table, and whatever range ID is given to that range, we need to just replace the salary value with that ID for that bucket. So here is the thing it will happen. So E tuple is representing the entire encrypted tuple name and salary, and bucket ID is representing for which salary we are allocating the bucket identifier for the bucket. So for example, the first salary is 54,500, and here you can see the ID is XR2K percent S in the bucket table, and the same ID is also here in the bucket ID part, and we can perform the same operation over the entire data set, and entire data set will get different bucket ID. Now, if a query will come for any type of selection query, for example, this range query. So what we need to do, we need to convert this range query for bucket ID. So the database owner has this entire bucket information. It will maintain, it will replace the 90K and all 100K where they are in this bucket ID list. And now instead of asking this range query, it will ask, okay, give me these bucket IDs. So this will the question will from the range query, it will convert into a simple selection query that give me this bucket ID 1 or some whatever is written here, or bucket ID this one. Server will see this bucket ID operation over the encrypted data set, and it will return the rows. So here by this way we can execute the range queries, and now if we are able to execute the range queries or finding the bucket ID based on bucket ID, so user is downloading only some part of the data. After downloading this data, if there are two tables based on bucket ID, it can also download different buckets from two tables, and it can also perform join operation at the local end side. So by this way, bucketization techniques can support join and aggregation or any type of queries by downloading only a small part of the data. So for this query, we fetch these buckets and so on. But here the question is, when we fetch lots of data using bucket can contain significant false information, and user needs to decrypt it and then filter the result before executing the query. So it creates some overhead at the database owner side. So as the positive side, these techniques provide most of the SQL queries we can execute because we are downloading some part of the data instead of downloading the entire data. Second part is this, on the bucket ID part, server can maintain the index by its own. There is no need for a database owner to ask, build the index and then send to the server. Simply, server will consider this as a column, ID column, and it can create a index and it will work. Any update operation in a server can do by itself. So this is the advantage, yes, part of this approach. However, there is some overhead, as I told you, that we DB owner needs to prune significant rows. There are some other techniques are also there that uses bilinear map or searchable encryption based techniques or Bloom filter for the join operation over the encrypted data. So right now, this is the last slide for the encryption based techniques. So I told you about some order preserving techniques that are fast but reveal the values of the column, and it is good for the maximum queries, minimum and range queries. Searchable encryption techniques are very good, as you saw in that part, that can execute for simple keyword queries, but they can reveal the data distribution as well as the access pattern. On the other hand, bucketization technique can support multiple types of queries, but user needs to download some additional data, prune it, and then execute the query at their end. Based on these techniques, different types of searchable encryption, order preserving encryption, and homomorphic encryption system have been developed. So first one was the CryptDB, that was using deterministic encryption and order preserving encryption. And as I told you in the slide of order preserving encryption, they were the first one, and they did not think about it how to use properly order preserving encryption over a column. So in CCS 2015, some paper proved this part that CryptDB, while it is good for executing most of the DB operation, but they are not providing security at all. Adversary can learn entire dataset in clear text because of mixing two or multiple techniques over the data. So whenever we mix multiple techniques, we need to be very careful. Otherwise, this will reveal some more information or almost the entire data set. What are the open issues that someone can work on based on encryption techniques? First, open question is there is no indexable technique that we can update index by its own, and there is lots of update operation is happening over the data. Can we develop any indexable technique that can deal with dynamic operation? Second open question is join queries. There are some, as you saw in the last slide, there are several papers on the join operation, but most of the techniques are not very efficient. Either they can deal with very small size of data, for example, in bilinear map approach, they can deal with they can join only 35 MB of data, and 35 MB data is very small, so of course they can do very fast. But if we have significant large part of data, how we can develop a efficient technique that can deal with different attacks in join case? This is still an open question, and someone can think to solve this problem. Second part is the secret sharing based technique. The
So
second
Shantanu,
category of
maybe before you go to
Mhm.
the second category, there is a question
Mhm.
from Shweta. She's
Yeah.
asking, what is the percentage of false positive in bucketization?
Okay. So in bucketization based technique, the false positive depends on the size of the bucket. So let's say I created only two buckets over my entire data set, and data set is, let's say, 1 million, and I partition entire data into two buckets. So whenever a single query will come, I need to download half of the data. So this is not very efficient. So the selection of the bucket impact entire performance of the query as well as the false positive thing. If there is only single bucket, or two buckets, we need to download significant data, and then we can process it at the database owner side. However, on the other hand, if we create bucket only for two rows or some very small values, then it is also not very good, because at this time the DB owner will maintain the bucket list, that which values are in which bucket. This will grow significantly. So whenever we use bucketization based technique, we need to balance where is the how much data DB owner can maintain, the bucket ID information, and how much information we need to retrieve. Does it make sense?
Yes, Shantanu, to me, I think so. If there are any questions, I'll ask you again. Hope Shweta.
Okay.
Yeah, okay. So she said it does make sense. Thank you.
Mhm. I cannot see any question where they are posted.
So
Okay. So
because you
this
have,
is a
yeah, it'll be on the
yeah,
Q&A.
yeah, yeah.
Yes.
Okay, now I can see. Okay. So now let us go over the secret sharing based technique and how we can use this thing. So these techniques, first of all, different as compared to encryption based techniques. So in encryption based techniques, you often user use is key that is used to encrypt the data, and this key is also used to decrypt the data whenever the query has been executed and user got the result. And as I told you before, that a powerful adversary can break the encryption system. For example, around 2 or 3 years before that, we know that hashing technique, they are completely, we consider that they are completely secure, but Google broke it. They reversed back, from the hash digest, they got the actual text values. So that's why we call it, these techniques are computationally secure. Means if adversary is having the limited computational power, they don't have any quantum computer, they cannot break our encryption technique. On the other hand, that now we are going to see secret sharing based technique, they are information theoretically secure. Even regardless of the computational power of the adversary can never break the underlying data or the underlying ciphertext. So these types of technique provide much high level of security, and data will remain secure forever, regardless whatever we techniques we can design to break the underlying cryptographic mechanism. So what happens in secret sharing? So this is the high level idea of secret sharing. So let's say on a graph paper, I give you a single point and I ask you a question that how many lines you can draw. So the of course the answer is from one point a user can draw multiple lines and they can go anywhere. Infinite number of lines, not multiple. However, if I give you only 2 points on the line, then the answer is definitely there will be a single line we can draw passing through these 2 points. And whenever this line crosses the y-axis, this is the secret value. So for example, if I have secret value 5, I can draw a random point, random line passing through 5 and pick any two values that can behave as a secret share. So let's see here in detail. uh, so suppose is the database owner. Alice has value 5 and she wants to create secret shares of 5. What Alice will do, Alice will put the secret value 5 at the y-axis. So she put value 5 at the y-axis and draw any random line. At this time, she can get random completely. So here you can see one of the random line. On this random line, she can pick any two random points. So for example, she selected one random point 9 and another random point 7, and she give this one value to one user or one server Bob and another value 7 to another server Carl. And it is assumed, it is considered, not assumed, it is considered that Bob and Carl will never communicate with each other. If Bob and Carl will communicate with each other or they will collude with each other, they will know the secret value that Alice is storing. So unless they will not collude, these two servers will not collude, they can never know what value Alice has stored. And now whenever Alice wants to get the value back, what Alice will do, Alice will ask Bob and Carl, okay, whatever values you are storing, give me back. And Alice will perform Lagrange interpolation and get the value back. So this is the idea of the secret sharing based technique. So here is some mathematical thing. So let's say if f number of servers will collude, like Bob, Carl, Adam, John, different servers or different people will collude. So then in that case, we need to select the degree of the polynomial larger than the number of colluding server, at least f plus 1. And if none of the server will collude, then polynomial of degree 1 is completely good. Another advantage of this technique is this is fault tolerant. So because we are creating multiple shares, so if one of the server will die, we can get our data from other combinations of the server. So here is another picture for the secret sharing based technique. So suppose the database owner has a secret value s, and it perform a simple polynomial operation to create the secret value fx equal to s plus ax, 1 degree polynomial, and it creates 4 different shares, and each server is not colluding with any other server. So all the server s1, s2, s3 and s4, they cannot learn the secret value at this time. So, and whenever the database owner or the secret owner wants to construct the secret s back, it can download the secret values from any two servers. So in this slide you can see from s1 and s2 she can download. Next slide, or she can download from s2 or s4, or any other server combination will work for reconstructing the same. And the other part is this is just a simple secret sharing technique. And there are also the technique order preserving secret sharing. These are similar to order preserving encryption technique. So what happened in order preserving secret sharing technique, that server can manipulate some relation less than, greater than or equal between the encrypted ciphertext. And here server can also execute such operation which secret share value is less than or which secret share value is greater than among these values. So server can perform these types of operation, and it will also execute the maximum, minimum and range queries. So for secret sharing based techniques, at the very high level, we can classify these techniques into two groups. One group is where they assume that server will communicate with each other. So for example, Bob and Carl will communicate with each other. And another technique is that where the server will never communicate with each other. So let me go over the first category where servers communicate with each other. So here you can see some papers I mentioned here. So it is assumed that server will communicate during during the computation, but they will not collude with each other. Means server 1 will not send all the shares to server 2, or server 2 will not send all the shares that it is storing to server 1. But whenever they are executing some computation, they will execute some computation. Whatever result they are performing, they will get after the computation, they will send to the second server, or the second server will send to the first server. So in this way they will communicate. On the other hand, non-communicating server, in these categories, server will never communicate, either before the computation, after the computation, or during the computation. So if you can imagine that these techniques, non-communicating server-based technique, they provide a high level of security, because servers, virtually we can say this thing, they don't know each other, so they cannot communicate also. And both of the techniques can support selection and aggregation queries very efficiently. Still, as I told you in the in the encryption part, joint operation, this is open problem in even in entire cryptographic domain. So here is no efficient solution for joining even two relation. Non-communicating servers, since servers are not communicating with each other, very good, secure, as well as no overhead. However, in this side, significant communication overhead, and moreover the communication cost will be according to the linear in terms of the database size. So this is the quick overview of the secret sharing based technique. So these are, I am not going over any database processing based system, but in the last slide I mentioned some system, so you can check those papers, or you can check the detailed tutorial of this in ICD. At the now the pros and cons of secret sharing based techniques. So as I told you in the beginning of the secret sharing based techniques, these techniques are information theoretically secure. Any adversary, regardless of the computational power, they can never break the underlying data unless they can collude all the servers that are storing the data. However, there is some communication overhead. Of course, if servers are communicating with each other, definitely there is communication overhead. On the other hand, that where the server do not communicate, the communication overhead comes between the DB owner and the server, but communication overhead is there. Another part is, someone can think about it to solve the join queries, how we can design a efficient encryption secret sharing based technique to support join operation, and then can we design a nested queries. Next part that is, I forgot to mention here, indexing. So most of the secret sharing based technique, they are not designed to support index. So the technique that I mentioned in the last slide, they are not supporting index. The cloud needs to perform the operation over the entire data set. So can we design any indexable secret sharing techniques? And the only drawback of this part is this: we need more than one server. So we need to pay some more money to Amazon or Google for storing our data. Next part is the so this was the end of the cryptographic based techniques. As I told you, two categories: encryption based techniques and secret sharing based technique. Next one is the secure hardware. So they don't use any encryption based techniques, and now internally inside SGX or the secure hardware, they process our queries. So first of all, what is secure hardware? So Intel SGX, this is the most famous secure hardware system that is available to all of us in present. The full form of SGX is Secure Guard Extension. They provide some secure memory inside the main memory. So what happens in this? You can see as this is the entire main memory part, and some part of the main memory is reserved, and no one can access this part of the memory. So whatever operation is happening inside this memory, any application that is running outside of this part in the main memory, they cannot see, or any other part of the kernel, they cannot see what is happening inside the enclave. So this is considered to be secure. And whenever we outsource our data to cloud, we encrypt it, and before executing the query, we verify that enclave or secure hardware part, this is completely secure. So there are some remote attestation mechanism that verifies that enclave is completely trusted. There is no bug in the enclave, there is no hidden code inside the enclave. So user can verify this entire part and then execute their operation inside the enclave. In the beginning, I told you that there are some side channel attacks on the enclave based on the hardware. So these are the some papers, recent research paper that presented several types of attacks. For example, based on the page table attack or the cache line or DRAM attack or the speculated execution. So based on these things, adversary can learn not all the data set but some part of the data it can learn, means it can know the access pattern, which row are satisfying the queries, or which part the output size attack it can learn. So these types of things based on the side channel attacks, adversary can learn something about our data set. So for example, in page table page fault attack, whenever we take any if else loop where either this is matching with our query or not matching, adversary can know immediately that which value of your query is matching with which row of the data, even if it is executing inside the SGX. And this is the result. If we so on the left hand corner you can see that these are the original images of something, and if these attacks are happening over the SGX, adversary can recover most of the part of the data. So images, he cannot know exactly how identical is the image, but he will know some information about the images. So this is happening because of these side channel attacks. So it is revealing some information about our data. So now the question is this: how we can develop any system that can support database operation using Intel SGX. So if we use SGX as a black box, we are sending our data in an encrypted manner to SGX and ask, okay, please execute our query. After decrypting the query, they are not secure. As I show you in the last slide, adversary can see just observing the cache line page table that what is happening over the data. So now we need to develop some oblivious operators for the SGX. So internally we will execute oblivious operation in over the clear text, such as oblivious sorting, biotonic sort, or column sort. So these types of operation we need to develop, or we can use any existing approaches, so that whenever we execute oblivious operator, then we can have some type of security. Then adversary cannot learn most of the data that we are executing. But again, there are problems of output size attack. This SGX cannot deal with these types of things. However, whenever we use oblivious operators such as oblivious sorting, so suppose I want to find a maximum value. So here, if SGX will take the data, decrypt it, and simply execute the maximum query. The adversary will immediately know which row. Let's say there are 100 rows in the data set. So adversary will immediately know that, okay, let's say the 50th row is having the maximum value. So adversary will know this part. For overcoming this part, we can use oblivious sorting. So oblivious sorting will result either the first value or first row or the last row is containing the maximum value. But here is the problem: if I use oblivious sorting algorithm, the cost is more than order of n. So if my data set size is very large, how we can develop efficient oblivious operator? This is the question that we need to solve. Second part is this: if my data set size is very large, let's say more than the size of the SGX memory, so some part of the data is inside SGX and some part of the data is outside of the SGX, and I am executing, let's say, selection query. So how we can execute now selection query over half part of the data? So if I return some answer from the first part that is inside SGX, adversary will learn. If I will if I will not return anything after fetching the second part of the data that is still in the disk, adversary will see this thing immediately. Okay, from the first part you return something, and from the second part you are not returning anything. So again, how we will deal with very large size of data set? This is still not solved. So right now, because of time, I cannot go over the details of any SGX based system. But here I mentioned some system that uses SGX and Opaque by UC Berkeley. This is a very popular system. You can download the code of Opaque also, and it can solve most of the SQL queries that you want to execute. Other system you can see here, VC3 is by the Microsoft, and for Versita DB is in last year in Sigma. However, all these systems, they are assuming something wrong. What was something wrong? They all are conceding that SGX is secure against all types of side channel attack. That adversary cannot learn anything either from the side channel attack or the page table attack or if else attack or anything. So this is the wrong assumption among these different types of systems. So still there is an open question that can we develop a system for the current SGX. Right now we are waiting since last 5-6 years that Intel will produce a new SGX system that is not prone to this part, but we don't have. So can we develop a new system that is also secure against side channel, different side channel attack for this particular hardware? Now the last part is data partitioning based approaches. So now we have seen cryptographic techniques and techniques for the secure hardware. And at the beginning, I show you this part that both of these techniques, they are not highly scalable. They cannot deal very large size of data. So what are the possibilities that we can use cryptographic techniques or SGX based techniques for a very large size data? So there are two scenarios. One is for the hybrid cloud and one is for the public cloud. And this is the same picture that I show you, that these are the cryptographic techniques. The last three bars you can see, these are for the cryptographic or SGX based technique. They are not very scalable. So the answer is the partition computation. If we can partition our data into two parts, sensitive and non-sensitive, then we can definitely scale our computation, because now we need to execute either the encryption based techniques or secret sharing based techniques or SGX based processing only over the sensitive data, not over the entire data set. And once the database size is reduced, we will not pay too much overhead for executing the cryptographic techniques over the non-sensitive part. So these are the techniques for the two types of thing. First one is the hybrid cloud scenario, and the second one is the public cloud scenario. So in hybrid cloud scenario, the private cloud will keep the sensitive data at their end and only outsource the non-sensitive data to the cloud. It will execute whatever queries he wants to execute over the sensitive data at their end and fetches only the non-sensitive data from the public cloud. And several papers are there in Sigmod and CCS over this part. Another category is the public cloud, where we are also outsourcing non-sensitive data in clear text to the public cloud, and we are outsourcing sensitive data in encrypted manner to the public cloud. And in this way, both data sets, one is the small size data set that is in the black color, you can see for the encrypted data or the secret share data, and the non-clear text data for processing over the public cloud. So this is the public cloud setting that is keeping both types of data set. So let's say partition computation over the hybrid cloud scenario, how the computation works. So here is the thing I am showing you in the context of MapReduce. So MapReduce is very popular thing that can produce a large amount of data. There are some mappers that produce some key value pairs, and finally reducers, they produce the final results. So here is the thing. So let's say data is at the both side, public and private side. Mappers produces the some key value pairs, and reducer download the entire data set from the public cloud, and then finally is producing the data. So here is almost it is fetching the entire data set before producing the answer. This is not very efficient, but something is happening at the mapper side. So whatever work that mappers are doing at the public cloud, user doesn't need to perform this type of work. Second part is this: we can also outsource our reducer to the public cloud side, and here whatever is the non-sensitive data that mappers can produce, we can also outsource the non-sensitive part after the mappers operation to the public cloud, and reducer can perform the work and send only significant reduced amount of data to the private side. So as compared to the first part, this approach is much better in terms of the communication cost. And the second part, we can use so in MapReduce, system, there is a concept of combiner that can combine the result of two systems from the mappers and reducers. They combine it and then send the data. So here we can use the same concept at this side. Instead of sending our non-sensitive part to the public cloud after the output of the mapper, we can combine the result at the local side and then get the data from the public side and combine at the private side. And last part is this: if there is no need to perform any type of computation at the local side for regarding the public data, then we don't need to download, just execute our computation and keep the final result at the public side. And this is just one way of the second picture that you are seeing on the top right hand side. And now let me go over very quickly over the partition computation over the public cloud. So let's say there are two databases, and here, so the red part is showing that the data set that is an encrypted part, and the green part is showing the non-sensitive data. So I partitioned these two data sets, and now one is encrypted and another one is not encrypted. I want to execute a query. Query will be executed over both data set, and it will return answer from both data set. Answer will be merged because this is containing answer from both sides, and it will produce the final answer. So this is just overview of the how we can process the query. Now let's see how the leakages will happen if we execute this type of computation. So let's say the query wants to retrieve all the rows of John. So what will happen after this? Adversary will immediately know this thing, that from the sensitive part, I am returning T2 row, and from the non-sensitive part, I am returning T6 row. And since adversary right now knows that, okay, I am returning rows for John, because adversary can see the actual query because of the query execution over the non-sensitive part. So he knows that the query is for John. Based on this, he will also know immediately that T2 row of the sensitive data, this corresponds to John. So when we were not executing any query, everything was secure. But once we execute a simple selection query, adversary immediately knows that second row corresponds to John. And John is the person who works in two different departments, in sensitive department, that is security, and in the non-sensitive department. So this is the some leakages happening here.
Shantanu, we are almost ending. I mean, it's almost 10. So if you can wrap up quickly, maybe.
Yeah. I am only 2 or 3 slides more.
Sure.
Within
Go
1 or
ahead,
2
please.
minutes. Yeah.
Please.
Okay, so next thing is, if we use axis pattern hiding techniques from the sensitive part, adversary will not learn anything, but still it will know, okay, something is returning from the sensitive side. Based on the output side, he will know something. And now to deal with these things, we need to deal these two new security properties. We don't need to we need to provide some security property that adversary cannot link between sensitive and non-sensitive part, and within the ciphertext he will not know anything. And finally, the conclusion part, we have multiple techniques. We need to see what types of operation we want to execute, and there is no such technique that can provide everything to us completely secure, no overhead, and full functionality. So on the landscape of different parameters, we can place different techniques, but combination of techniques such as CryptDB is using, I told you in one of the slides, we can design a better efficient system. And I discussed several things here. So encryption based techniques, secret sharing based techniques, SGX based systems, and can we expect secure mediation, means how we can use multiple techniques over one database, just like CryptDB, in an efficient manner. And several people help us to work over these different parts of data. Some professors, my PhD advisor Shlomi, my friend Yen, Nisha, Jeff Ullman, and Nalini, and several PhD students also help in developing approaches and in slides making also. So thank you. And if you have any question, please email me, and slides are also available online.
Hi, Shantanu. So thank you so much. Thanks for a great session. But before we end, I think there is a message to play from one of the sponsors. So Atul, please, will you please stay back.
Harshit Khadilkar, and I am a senior scientist with the Data and Decision Sciences group at TCS Research, and I am also affiliated in a visiting capacity with IIT Bombay and IIT Madras. Today I'll be talking about the future of AI in enterprise decision making, which in a small way we are working on in the Data and Decision Sciences group at TCS Research, which itself is one of the many research areas that TCS Research is focused on. So what my team focuses on is deep reinforcement learning algorithms for improving industrial system efficiency efficiently. And when I talk about that, what I am talking about first of all is improving the efficiency of industrial operations such as logistics or transportation systems, and doing it efficiently, that is with fewer computational resources and smaller training times. So we focus on lightweight explainable forms of reinforcement learning that include rather than exclude domain expertise which already exists in these systems. So we'll use domain expertise for feature engineering as well as to work with existing heuristics in the area. And this is essentially what we are focused on. So today's systems have a lot of sensors which measure big data, have IoT applications running on them, etc., which generate a lot of features, and these are sent to existing machine learning or AI algorithms which generate forecasts or alerts, predictions about what the system will do. And these alerts are presented to a person who then uses his or her intuition and experience to decide what action needs to be taken on the system. So while this is useful and valuable, the person's experience is valuable, it's not ideal in normal operations because we are looking for things where things go wrong, and that is when the person's intervention is required. But in day-to-day operation, you are not really trying to fatigue or tire the person out. So like I said, in state of the art, you either have heuristics which are rule-based systems which make fixed decisions based on a given problem instance and give you fixed solutions. So there is no scope for further improvement. Or you have meta-heuristics such as genetic algorithms or simulated annealing, where you have curiosity, exploration, improvement, but it takes a very long time for these methods to produce solutions. So we want the best of both worlds. We are using human knowledge and curiosity and exploration to create this aggregated intelligence using offline training, which is then put into the AI algorithm so that when a new problem instance is given, you get a one-shot solution out of it. So a concrete example is something very simple that everybody understands, the capacitated vehicle routing problem. So the problem here is that you have a fixed number of vehicles sitting in your depot in the center of the screen, and you have a number of customers which need to be serviced with a given quantity of product in a certain amount of time. And so this can be solved very easily once it is quantitatively put together, but this is not a very easy task. So there are complications such as people coming in and out of the system. So you have pop-up customers who might leave when their timing is too long. Every day is different, so the customers are different, their locations are different, and so on. And there are a lot of business rules such as when vehicles can travel in a certain area of the city. So forming the problem itself is an art form rather than a quantitative form, but once the problem is formulated, then it becomes easier to solve it. And so these are the kind of things we are focused on. So specifically, the gap between theoretical research which gets published and the kind of practical work that we are trying to do to make a real world impact is, first of all, that unlike in published research, we don't have very compact representations of the environment. So it's not easy to write analytical or simulation based environments. We also have variable or very large dimensions, much larger than any typical game. So unlike in the case of chess, where you have a fixed 8x8 chessboard, we have, in the case of railway scheduling, any number of trains traveling through a very large number of stations. We do not have access to unlimited computational resources, so we cannot use the kind of compute that very large firms, some of the famous papers in literature use. We have to use reasonably small compute, and any results that we produce have to be acceptable and explainable so that the person who is using these results can actually trust the algorithm. And this is where many existing algorithms break down, and so that is the kind of challenge that we are particularly interested in. So this is an example of something we have done. In the COVID lockdown, we saw that there were a lot of decisions about district lockdowns or unlock happening without too much quantitative justification. So one of the things we did was create an environment which emulates the spread of disease through the country, and then try and see if a reinforcement learning agent can observe these parameters in real time and make quantitatively justifiable decisions about whether a district should be locked or unlocked. Similarly, we have used similar concepts to do recovery from railway delays. So we know that in a railway system, secondary delays can spread very quickly. One train breaks down, it delays others, and those other trains delay others, and so on. And we found that reinforcement learning gives us a very efficient way of recovering from such problematic situations. In bin packing, three-dimensional bin packing, which is an online version of the problem, we have used reinforcement learning to decide where parcel should be put in the best possible location so as to maximize bin volume utilization. And we don't just stick to single agent systems. We have worked on multi-agent reinforcement learning problems, such as in this case in a supply chain, to make sure that all the stores and warehouses are stocked to their current inventory levels so that the customers always find the products that they are looking for on the shelf, but they don't send so much product that any of the perishables go to waste. And this work in fact is part of TCS Optumera, which is a real world product offering. And it's not just application based work that we do in TCS research. We also have fundamental questions about the efficiency in which sample efficiency of reinforcement learning, as well as handling delayed algorithms explicitly, and of course training latent representations in a deep reinforcement learning context, making sure that the networks learn a very robust representation of whatever they are observing. So all of these are studies that have appeared in main track papers. And so from here, we are looking to go in 4 directions. The first is, can we use AI not just for correlation based techniques, but for actual reasoning using causality? Can we use active learning to get the agent to come back and ask for help when it doesn't know what to do? Can we have self-trained algorithms which don't depend on previously collected history? And of course, what can we do with offline collected data in cases where we don't have access to simulation algorithms? So the future of AI, in my opinion, is going to be along these 4 directions. Thank you for your time.
Thank you, Harshad. Is there any question for Harshad? Please now is the time to ask, I guess.
I don't see any question, but Harshad, if maybe you want to add something just in the end, and then.
Yes.
Sure. Thank you, Atul, and thanks for handling the logistic issues. So I just wanted to add that obviously this was a very small part of what we do in TCS research. In 8 minutes, I could only focus on a few decision-making areas, but I just wanted to emphasize that there is a lot more happening in all areas of research, from life sciences to computing sciences to foundations of computer science and so on. And I think there's an overview talk also coming up on Sunday that describes all of this in more detail.
Okay, so the
So,
one attendee is asking,
yeah,
raising a hand. Yeah,
exactly.
normally we post the question in the Q&A, but maybe as an exception, we can. Okay, I think.
Yeah, I think he has
I can.
again.
I can hand the mic. Yes, just as an exception. So you can ask the question quickly. And
Okay, I think he
Okay, I
has
think
dropped
gone.
again.
Okay, that's
Yeah.
okay. Then we
So
can
if
end
there's
it.
any question, please message Harshad personally, or I think in this airmeet, you can actually directly personally message. So please go ahead and ask your question to Harshad.
Yeah.
So I really thank you for the fantastic tutorial. Shantanu, is it possible for you to switch on the video, please? Great. Yeah. So thank you so much. Yeah. Thank you so much for the fantastic presentation, and thank you for keeping it in time. Thank you all the attendees. I think throughout the session we had an average of 30 attendees, so that's a great participation at 8:30 in the morning. Before we end the session, Harshad, Shantanu, I am just going to take a screenshot because we cannot really take pictures at this moment. So
Sure.
I'm just taking a screenshot. Yeah. Okay. So thank you so much. I think we will end the session now. Thank you all. Thank you, Shantanu. And I hope Shantanu, Harshad, and all the participants, please stay back for all the other tutorials that we have today. Thank you so much. So Atul, please end the session. Yeah. Thanks.